Let's find the volume using the disk method. We will implement two methods in this chapter. The first is the disk method, and then the next would be the shell method. You could say it's three methods because within the disk method we are allowed to use the washer method. And the washer method is simply a disk with a hole in it, and so you want to subtract the hole, the empty space from the so-called volume. Here we calculate the volume of a solid that's being rotated on some type of axis. Various solids that we will consider. The key to calculating the volume using the disk method is to be able to calculate the rectangular slice. Here, the rectangular slice would give us, if you will, the so-called area, and then from that area we will multiply it times the width, and we get ultimately the volume of the disk. So here the volume of the disk is the area of the disk times the width of the disk. And correctly, let me make sure I say it accurately, the rectangle gives us the so-called width of the disk. And then from the graph we're able to determine the area. So here's an example of a disk that's being rotated on some axis. So we calculate the thickness of the disk, and we get that from this rectangle, this rectangular slice. That gives us the height of it, gives us the radius. So we'll need that radius squared times the width. The width would be either dy or dx times pi, and that gives us the volume. This definition of the volume is defined as the summation of pi times the radius to be squared times delta x. We can talk about the so-called volume of the disk either with respect to the x-axis or the y-axis, or given any other type axis. You can rotate a volume of a solid about any axis that you may choose. So if the axis is horizontal, then we use the so-called volume with respect to x. If the axis is vertical, then the volume is found with respect to y. And then graphically, I want you to notice that if you have an axis of revolution, then the radius is always perpendicular to it. From the radius, you look at the thickness and you're able to denote if it's going to be dx or dy. So here, if we rotate a solid on a horizontal axis, then you always use dx. If the axis of revolution is vertical, then the radius is perpendicular. The thickness of the radius is with respect to dy. The washer method, if there's a hole somewhere that you have to take out, so you calculate the overall radius minus the small radius. You put that into the same formula, and so we have a gap there, so it's pi times the integral of the radius, capital R, the big radius squared, minus from the washer method the whole part that you want to exclude, little r squared dx. Now, I put some steps in here for you to use when you're looking for the volume for the disk method. You want to graph the given equations. From the graph, determine the radius. The radius will always be perpendicular to the axis of revolution. I put that here as a statement because in the next section, the shell method is the reverse. The radius is parallel with respect to the axis of revolution. But here for the disk method, the radius is perpendicular. Number 3, the thickness of the radius determines dx or dy. I somewhat stated that in the graph from the previous screen. If the thickness is parallel to the x-axis, then you're going to use dx. If the thickness of the radius is parallel to the y-axis, then use dy. Looks like I'm leaving off an E there, excuse me. From the graph, determine the limits of integration. If using the Washer method, then you must locate and be able to distinguish between capital R of x and little r of x from the graph. Then from there, you want to set the volume up, the volume equation, and then solve. Let's consider some problems from this section.